Welcome back. Happy Wednesday. This will be for module number 17, and I'm going to film two very short little clips, one for this module and one for module 18 back to back. You might choose to watch both of them and sort of do both of them at the same time because it's all one concept. We're going to be covering, now watch this, page 17 all the way to page 24, but please don't print out all these notes. You'll notice that when Van Beek created this unit, he made it so that you're working towards being a bit more independent in grade 12, and you'll find that that's the case, that there's more sort of learning on your own. Well, now, because of this distant learning, you're all actually really good at learning on your own. So you probably won't need my help too much for these ones. And that was really kind of the point. By the time you're in grade 12, you learn to be more independent and you're actually pretty good at learning, all right? So I'll set it up for you and then I'll let you know, or you let me know if you have any further questions about this. But this is all about calculations. And remember, when you're looking at numbers in chemistry class or any science, put meaning to those numbers. And then once you understand what that number means, you understand the concept quite a bit better, okay? Remember I talk about that a lot when we're doing anything to do with units, like what is the rate, what are the, converting of moles, or doing our stoichiometry calculations. This is another one of those concepts. If it makes sense to you that if you're calculating a value where you've got a number on the top and a number on the bottom, if the number on the top is bigger than the number on the bottom and you're dividing, you're going to end up with a bigger number. Okay, if you have a smaller number on the top and a bigger number on the bottom, then clearly you're going to end up with a smaller number. And so just looking at that ratio of how the numbers work, I think will be helpful for you for this concept, okay? So what we're doing is we're calculating K. K is the equilibrium constant. Okay, so it's taking an equilibrium expression and then it's looking at the concentration of the reactants and products, putting them into a formula and looking at what that value is, okay? And if that value, okay, if you can see down below in the little video right over here, that K value, which is the equilibrium constant, if your concentration of the products is the same as the concentration of the reactants at equilibrium, multiply the values out and you're going to get an equilibrium constant of 1. Mathematically, that should make sense. So what we can do is we can look at a system and we can figure out, is the system at equilibrium or not, based on is that K value actually 1. If it's less than 1, then it's favoring a certain direction. If it's greater than 1, it's favoring another direction. And if it equals 1, then that system is at equilibrium. So this is all about calculating K, which is the equilibrium constant. I'm going to watch Mr. Bozeman's video, or Mr. Anderson's video down below for about a minute because I want you to see the PHET simulation. I can link that simulation if you want to give those a try, you can, but sometimes it's easier just to watch the video and get the explanation. So here you can see reactants are going to be green, products are going to be red. Imagine these gas molecules in a closed system. So you've got a dynamic system that's at or approaching equilibrium. And he's going to talk to you about calculating K. Here we go.
So I've got this model right here that shows us how reversible reactions work. So there are going to be a bunch of molecules over here. We'll call those reactants, and they'll be green when they're on this side of the chamber, and they'll be red when they move over to the right side. This is a PHET simulation. Over to the right, I've created a K-ometer, which is going to measure our K value. So K is going to be the number of products divided by the reactants. At this case, we only have reactants on the left side, and so we have a very large number here, 100. And how many products do we have? 0. And so what's our K value going to be? It's simply going to be 0. So let me start this and see what happens to our K value. And so molecules are moving now from the reactant to the product side, from the product to the reactant side, but we basically have the same level on both sides, and so our K value is 1. Now as I tip it towards the right, we're getting more products, and so that is going to become a larger number up here, and so our value goes up to 3. We have about 3 times as many products. Likewise, when we pull it in the other direction, now we have way more reactants, and since our reactants in this case value is going to be around 75, products around 25, our K value is going to be around 1/3. Now this model oversimplifies a little bit because we only have products and reactants in this simulation. In a chemical reaction, you're going to have lots of products and lots of reactants. And so if we've got a reversible reaction like this, where this represents our reactants and this represents...
Okay, I'll stop it right there because I'm just going to show you the exact same thing in our notes, but that's how you're going to set up the constant value to calculate the K. Okay, so here we go. I guess this is as big as I can get it anyway. Okay, all right, so for the equilibrium constant, again, this is what we're going to be calculating. And it's module 17 and 18. It just covers pages 17 to 24, so feel free to go do them both at the same time if you'd like. When you're calculating K, okay, sometimes you'll see it as KC, sometimes you'll read it as KEQ. That is the exact same thing as K. You just may read it in the textbook as K equilibrium. That's K, okay? Can you see here, for a equilibrium system, you're going to set it up where it's the concentration of the products over the concentration of the reactants. And can you see there that you're going to add in, you factor in the coefficients as exponents when you're going to be doing your calculations. Okay, so hopefully you've got your calculator ready. You've been practicing using your math. We haven't done much calculation other than some easy heat calculations, right? We haven't used the calculator too much. All right, there's a few disclaimers. So this is the box that has all of the rules in it. Notice that the substances A, B, C, and D, you only add them into the equilibrium expression if they're in the gaseous state or the aqueous phase. Okay, there's a whole explanation as to why it doesn't work, why you don't need to factor in anything that's a solid or liquid. It's because that those concentrations always remain constant. All right. I summarized why that is over here. So go ahead and look at that explanation and look in your textbook if you want some more. Okay, but basically it just means that you got to look at the state of your reactants and your products, and you're only going to factor them in if they're gaseous or aqueous. If it's a solid or if it's a liquid, you don't even have to bother using it. Okay, the concentrations are all going to be moles per liter to keep things consistent. Notice that the little a, b, c, and d are the coefficients. That's easy. We'll plug that in later. And again, there's a little point right here that's quite important. Let me start that again. That K only varies with temperature. Okay, that's like a true-false question. It'll be on the quiz at the end of the unit. K is only going to vary with temperature. So when you calculate the K value, because we're dealing with gaseous and aqueous, you can put a little disclaimer, like this is the K value at 25 degrees Celsius, or this is the K value at 42 degrees Celsius. K will vary with temperature, but nothing else. Okay? All right, so how do we do that? Here we go. First question. You're looking at your equilibrium expression, and I want to take the concentrations that I have at equilibrium, and I'm going to calculate what the K value is, okay? I'm going to add in my hydrogen ions, I'm going to add in my acetate ions, and I'm going to add in my acetic acid because I've checked my states, and they're all needing to be added in, okay? So here we go. Take your concentration of your products, divide that by the concentration of your reactants. My molar ratio is 1 to 1 to 1. There's nothing else I need to add in for this one. Let's do the second one. Here we go. Calcium carbonate and 2 hydrogen ions to calcium ions, carbon dioxide, and water. First thing you do is you check the state. I don't need to include this one. I don't need to include this one, but I will include the other ones. Okay, so I take my products first. So I've got my concentration of the calcium ions, multiply that by the concentration of my carbon dioxide gas, divide that by my concentration of the hydrogen ions, and note right here that I take my 2 coefficient and I use it right here as the squared value. That will then calculate my K value. What is K? The equilibrium constant. Okay, here we go. I want to show you how these notes were set up to be self-learning and self-checked, in that all the answers are right here. So you can see that you've got a question, okay, and then the answers with a little T bar are right underneath of it. So it gives you some space for you to solve the question, and then it gives you what the answer is. So let me show you on page number 18. And this is why you don't need to print out all the pages. Just do a couple of these and then you'll get it, all right? So for the first one, you can see that you would calculate, all right? So if you wanted to do this one, I'm like, okay, I'm gonna include everything here, concentration of the products. I'm gonna add my concentration of the water to the exponent 2, multiplied by my concentration of the chlorine gas, to the exponent 2, divide that by my concentration of the oxygen gas, multiply that by the concentration of my hydrochloric acid to the exponent 4. That is what we call the equilibrium expression. That's how you're going to calculate the K value for that system at equilibrium. Okay, now, can you see here how you're going to do these questions 1, 2, 3, and 4, and then guess what? Just below, you've got all of the answers. So you can just simply self-check your answers. And if we were in class, it would just be like a work period. I'd give you a little preamble like this, and then away you go and solve all those questions, okay? If you have any questions about these ones, well, the answers are right here as well in the notes. So there's some further information for you right here, okay? So you're going to solve these, and you can again see here, this is the next type of question. So here we go. We're going to calculate the equilibrium constants given the equilibrium concentrations. So if this is your question here and you're calculating the K at equilibrium, what values are you using? You're using the concentrations at equilibrium, because using other concentrations is going to be like the next step question, okay? You're going to be looking at, does this, do these concentrations show what it is at equilibrium, or does it show a system not at equilibrium? And that's what we're going to be solving next, okay? So you take the values for equilibrium, pop them in, check your answer, okay? Gives you lots of practice here. And so page number 19, page number 20, and that's about it. I'm going to stop right here for this part, and I'm going to explain the relative size of equilibrium constant, and that's on page 21, and page 21 to 24 is going to be the next module, but I'm going to post both modules together in case you just want to work on it all at once. Okay, thanks, and we'll talk to you in a minute.